Hi, my name is Feynman, and today I'll be talking to you about fat-tailed variational inference with anisotropic tail adaptive flows. In variational inference, the goal is to approximate a target density pi given access only to a proportional auxiliary pi bar. For example, in Bayesian inference, one is interested in approximating the posterior p of theta given x, but due to the intractability of integrating the partition function, one only has access to the joint density p of x and theta. To perform variational inference, one maximizes the evidence lower bound, also known as the elbow. A more expressive variational family Q yields better approximation as it allows little q to be closer to the target pi. How can we make a variational family more expressive? One idea is to use push forwards under normalizing flows. So we will let f sub theta be an invertible flow, and we'll let p sub x denote a base probability density, and we'll consider the variational family obtained by pushing p sub x through f sub theta as theta varies. This is shown in equation 1, and in figure 1 we show the result of pushing forward a Gaussian through a series of normalizing flows. Here are some recently developed invertible flows. All of these flows are covered under our theory when they are Lipschitz. In fat-tailed variational inference, we ask the research question, what happens when the target pi is fat-tailed, and what about when it's multivariate fat-tailed? So as an example, in the top left, we've shown a target which is fat-tailed student t in the x direction and light-tailed normal in the y direction. ADV imposes light tails in both directions, whereas a previous method, tail adaptive flow, imposes heavy tails in both directions, neither of which is able to recover this tail anisotropy. In contrast, the method we propose, ATAF, is. In more detail, ADV consists of a push forward of a normal, whereas tail adaptive flows consists of a push forward of a product of student t's with the same tail parameter in every direction. And thus our work is a slight modification of TAF where we allow the tail parameter of each student t to vary across each dimension. Although this may seem like a trivial modification, our theory later will establish that this is indeed necessary to represent anisotropic tails. Our first contribution is the sharpening of prior univariate theory. Specifically, we show that normalizing flow push forwards cannot make the tails of a fat tail distribution fatter. And furthermore, if the normalizing flow satisfies additional assumptions, then it cannot even change the tail parameter of a fat tail distribution. And finally, we prove a result regarding polynomial flows, which states that light tail distributions remain light tails under polynomial flow push forwards. Our second contribution is a proposal for a multivariate fat-tailed theory, where we define this multivariate tail parameter function by taking limits of 1D projections along rays through the origin. And using this tail parameter function, we're able to quantify whether a distribution is tail isotropic or if it's not, like shown in this figure. Under our multivariate theory, we're able to prove the necessity of ATAF through this impossibility result, which states that given a tail isotropic base distribution, any of the flows considered previously will keep the push forward tail isotropic. Let's now move on to some examples. In Bayesian linear regression, we know that with conjugate priors, the posterior distribution is known to be tail anisotropic, since with sigma being power law and beta being sub-Gaussian. This is represented by the target posterior in the top row, where we see that sigma, being power law, is heavy-tailed and concave up, whereas beta, being light-tailed, is concave down. Neither ADV with its Gaussian-based distributions nor TAF is able to recover this anisotropy, whereas our method ATAF is. Another common benchmark is the 8 schools benchmark for Bayesian inference. Here we see that again, ATAF achieves the best approximation as measured in both elbow as well as log marginal likelihood. And finally, on financial and actuarial modeling tasks, both of which are known to have heavy-tailed data, ATAF again recovers the best approximation as measured in log likelihoods. So in summary, we've seen that flow-based methods can expressively model the bulks of complicated distributions. However, the modeling of tails is still limited by the choice of base distribution. Whereas prior work has considered univariate tails and products of student t's with the same tail parameter, in this work, we've refined the prior univariate theory to be sensitive to the tail parameter alpha, and we've sharpened the closure results to account for this. We've also proposed a multivariate theory to quantify tail anisotropy, and under this theory, prove the necessity of ATAF. Finally, our experimental results confirm that ATAF yields numerical improvements on several real-world datasets and applications. Thank you for your attention, and I hope you enjoy the rest of the conference.